reflections. Like with the shifts, we will start with a vertical reflection. The vertical transformations, as I mentioned, are typically easier because you do what you're going to do anyway and then make the change afterward. The horizontal ones, as we saw, the horizontal shift that we saw, we kind of have to work backwards. So we'll start with the vertical because at least it's direct. So what we have here is, again, one of our basic functions. This time I've chosen f of x equals x squared. We can use any of the basic functions. This is just the one I happen to choose. We then have g of x equals negative x squared. Now, let's not forget that that really is a coefficient of -1. So we've got this multiplication by -1, and by order of operations, it happens after the squaring of x. So, this, by the definitions in the PowerPoint, should be a vertical reflection. This should affect the y coordinates, which means x should be unaffected. So I'm going to take any old x value that is in the domain of this, and the domain of x squared is all real numbers. So I can pick literally any x value I want. And I'm going to put that same x value into both the original function and into the transformation function. Simple enough. 2 squared is 4. Now, in the function g, remember order of operations here, and that's part of why I wrote the -1 and the dot for the multiplication. We need to remember that that is a separate multiplication and the exponent has to happen first. So what we do is we produce the original output value, and then afterward we alter it by multiplying by -1. So what we get is exactly the same value but with the opposite sign, because all we're doing is multiplying by -1. So we will produce the original output value and then flip its sign between positive and negative. Whichever one it happened to be, it will now become the other. Let's look at another value. Again, I can choose any x value I want here because the domain of the original function is all real numbers. Let's choose something negative this time. Let's try -3. -3 squared, -3 times -3 is +9. We'll take the same input value, -3, and put it into the transformation function, where we will start by doing the same thing that we did in the original function. -3 times -3 is +9. But then we have a new operation to perform, and that operation is to multiply by -1, which produces the same value but with the opposite sign. Now, we're going to take a look at the graphs here, as we did before with these shifts, to compare them to see, to get a visual of what the difference is, but also to kind of see how this type of transformation differs from the shift. wish I had a bigger whiteboard. I already have a grid set up, so I wouldn't have to spend the time drawing it here, but this is what it is. So f of x equals x squared, one of our basic functions from our library. So we should be somewhat familiar with it already. It gives us this U shape, which is called a parabola. Now, as we saw, for any given x value, we put it into both functions and we produce the same y value but with opposite signs. So the range of x squared is 0 to infinity. We did not produce any negative values as outputs. By contrast then, this will only produce negative outputs, and of course 0. So let's use the points that we played with before, namely 2, which produced an output value of 4, but with g of x, it produced an output value of negative 4. We also used negative 3, which produced an output value of 9. In g of x, it produced an output value of negative 9. So what we've got here is that this point, which was once 4 spaces above, rotates or reflects to become 4 spaces below. Now, unlike a shift where if one point moved a certain number of spaces, they all moved that same number of spaces, that is not the case in the reflection. Picture a mirror, if you will. The closer you stand to the mirror, the closer your reflection is. But if you step backward, your reflection also seems to step backwards. So the further away the point is, the further away its reflection will be. So this is different from the change in position that we had in a shift. This is a change in orientation. The relative distances are all the same, they just happen in the other direction. So instead of 1 space above the x-axis, we would be 1 space below it. Instead of 4 spaces above, we would now be 4 below. Even this point, now that's an interesting thought, but again, if you think of a mirror, if you actually put your finger on the mirror, your finger and your reflection's finger are actually touching, the thickness of the glass notwithstanding. So that point actually doesn't do anything. Now, if you want to go through the math for that, all we have to do is use the x value of 0 in each one. But what happens when we multiply 0 by negative 1? We still get 0. So what we end up with is a downward parabola, an upside down U, if you will. Now, that takes care of vertical reflections. The horizontal reflections, we're going to have to change up which function we use here, because there are some functions like this one and the absolute value function where, and we'll get a chance to see this shortly, where if we do a horizontal reflection on it, it ends up looking exactly the same. That is an important and unique property, well, not unique, but an important property of functions that we sometimes need to be aware of. But for now, we'll use something where the change will be much more readily apparent. Now we have a number of functions in our library to choose from. We try to stay away from the linear function for several reasons, not the least of which being that it's so simplistic. It doesn't have its own base operation, like x squared or the square root of x. And also because, let's face it, this is pre-calculus. You learned about linear functions in Algebra 1 and you rehash them in Algebra 2. I think we've got the idea of linear functions, slope and y-intercept, down pretty well. So we kind of tend to shy away from that. I'm going to choose here another function though, the square root of x. Now, according to the definition of a horizontal shift, or horizontal reflection rather, that we saw in the PowerPoint, this should happen because there's a -1 coefficient that occurs before the basic function operation. So we do have, again, a multiplication by -1, but look at the difference in the order. Instead of performing the original operation and then multiplying by -1, this would have us take the x value and multiply it by -1 first. So that change in the order of operations, that change in when this multiplication by -1 occurs, means that even though it's the same operation with the same value, multiplication by -1, it has a different effect. So let's work with this in the same way we did with the horizontal shift. Let's recognize first of all that if this is a horizontal transformation, it has no effect on the y-coordinates whatsoever. And that means we should start with the same y value in each. Now, the range of this function is 0 to infinity, including the 0. So we can pick any non-negative output value that we want. So I'm going to choose 4. And we need to solve for x. So again, simplistic. If that was the entire goal, it almost seems silly to even do that, but the goal is to see that happen and then to see what happens with this. Let's try then the same output value. Now we're going to start the same way, just as we saw with the horizontal shift. We're going to start the same way by doing the same thing. And we're going to produce the same value at first. But that's not where we stop, because x isn't by itself. To finish solving for x, we need to divide by that -1. Once again, we see that kind of inverse relationship happening where this might be written with a multiplication of -1, but to interpret the transformation, we actually need the inverse operation. And what we get here is exactly the opposite sign x value. So where in the original function it's f of 16 is equal to 4, here it is g of -16 is equal to 4. Now, we do want to look at the graph at some point here, so we should probably recognize that positive 16 and negative 16 is a little bit far out to the sides on the graph, so let's pick something a little bit more reasonable, a little bit smaller. But let's try it again and see what happens here. So again, we're going to choose the same output value for both, because a horizontal transformation should have no effect on the y-coordinates at all. So this time I'll pick something a little bit smaller. How about 1? Simple enough. Once again, we solve for x, and not surprisingly, x is equal to 1. For g of x then, Well, once again, we solve for x, and we start the same way. We produce the same value, at least at first, but then we have an extra thing to account for. And that results in a different x value than we had in the original function. But same value, just opposite signs. So, we can take a look at the graphs of these. Again, using our knowledge of the library of basic functions, which is why we had that, of course, just so that we had some simple, very basic, as it said, very basic functions whose characteristics were very easy to identify and that we could then manipulate in different ways. So, let's take a look at these graphs. So, the first point we did was at a y value of 4, but we saw that had to go all the way up to 16 and negative 16, so not the best point as far as graphing is concerned. But let's again start with what we know, and that is that the original square root function goes through the points 0, 0, 1, 1, 4, 2, and 9, 3. Now, again, we don't get as far out as 16, 4, but we did have another point that we worked with, 1, 1. And what we saw was that for the same output value of 1, g of x had an x value of negative 1. So we get that same kind of thing we had going in the vertical reflection, except this time we're going across the y-axis. We're going side to side, horizontally. Now, this is, of course, a small distance, but if we went out to 16, that would be a much greater rotation. So, again, we see that difference from a shift in that not every point is moving the same distance because we're not sliding to the side. We are literally reflecting, or you could even think about it as rotating halfway around. So this point here, 4, 2, should be, instead of 4 spaces to the right of the x-axis, it should be 4 spaces to the 4 spaces to the left of the y-axis. And what we get is the same graph, but oriented to be leading out to the left instead of leading out to the right. So again, different operations cause different effects. And depending on what the value is, will determine what effect that is. If it's an addition or a subtraction, it will be a shift depending on whether it is before or after the original function operation will determine whether it is horizontal or vertical. A multiplication by -1, again, either before or after the basic operation will determine if it is a horizontal reflection like this or a vertical reflection. Coming up, we're going to be looking at what happens when we start mixing the different types of reflections. The different types of transformations. What if we have shifts and reflections in the same function? And we have one more transformation yet to look at as well. Stretches and compressions, or as I prefer to call them, distortions. So we'll see those in upcoming videos.